So as we begin Module 6, we're taking a look at the broad topics of extended surfaces and the bioheat equation. So within this module, we're going to take a look at the heat equation from extended surfaces, the bioheat equation or heat transfer within the human body, and then move on to discuss thermoelectric power generation and conduction on the micro and nano scale. Now we're going to break this into two different modules here. In the first module, we'll cover those first two topics here of extended surfaces and the bioheat equation. Then we'll continue on the next module 6.2, and we'll take a look at thermoelectric power generation and micro and nanoscale conduction. As we relate this back to our textbook, this goes back to chapter 3, sections 6 through 9. So in 6.1, the first section of this module here, we're going to concentrate on the extended surfaces. So an extended surface involves heat transfer by conduction within a solid and heat transfer by convection and irradiation from the boundaries of the solid. Now the direction of the heat transfer from the boundaries is going to be perpendicular to the principal direction of the heat transfer in the solid. Objectives within this module here, we're going to take a look at the general conduction analysis, talk about the Finn equation, look at some Finn performance parameters, then go from there into Finn arrays, an array of fins, and then from there talk about surface efficiency. So within this module, we'll go through the key and governing equations, talk about some practical applications, and then do some problem solving. So the first topic I want to discuss is the nature and rationale of these extended surfaces that we'll be getting into here. So let's just talk about basically what an extended surface is. So an extended surface, which is also known as a combined conduction convection system, or a fin, because we're dealing with both conduction and convection, as we mentioned in the beginning intro here. This is a solid within which heat transfer by conduction is assumed to be 1D. So that's going to simplify it down, considering it's one-dimensional, while heat it's also transferred by convection and or radiation from surface in a direction transverse to that of conduction. So that's important here. It's in a direction that's going to be transverse to what the conduction is right here. So we can take a look. We have this diagram down here. We can see our fluid off to the side over here for convection over here, and we can see we got, temperature T infinity and our H right here. Then we have these two surfaces at the top and bottom over here, T2 and T1. We can see we have convection across that right there. So the rate at which energy is going to be convected to the fluid from any point at the fin surface must be balanced by the net rate at which the energy reaches that point due to the conduction in the transverse, in this case X or YZ directions. So as we continue on to our nature and rationale section here, one thing we want to ask ourselves is how does our conduction heat transfer rate vary with X right here? What we can do is we can take a look at our governing equation 3.36 in our textbook here, and we get the following relationship here, that Q of X is equal to our negative conductivity, thermal conductivity here, times AC, times our dT dx, our change in temperature with respect to that distance X. So as our temperature changes here with respect to X right here, this is going to change our Q of X as well. Another question we can ask ourselves here is, when may this assumption of 1D conduction be viewed as a good approximation? Well, the case here that this can be a good approximation is when we're dealing with the thin film, the thin fin approximation. So these extended surfaces may exist in many situations, but are commonly viewed as fins to enhance heat transfer by increasing the surface area. So you see this in a lot of electronics where you have all these fins coming out here, and that is the purpose of that right there, is to enhance the heat transfer by increasing that surface area that is available for convection and or radiation. They're particularly beneficial when your H is small for a gas or natural convection situation. So again, you see this in a lot of electronics that overheat, so you put these on as kind of heat sinks in the back type of the electronics to increase that surface area there. So what are some typical fin configurations right here? Well, some typical fin configurations are shown here below in A, B, C, and D, where A is a uniform fin configuration. So you can see that there the whole way here. You got this W, this width here, and the thickness here, right this, as it comes out in our X direction there. Then we have B right here, which is a non-uniform cross section right there. So you can see this kind of tapers down, not uniform on the way out there. Then we have our annular fin right here, so it has some radius that comes out, some thickness right there as well. And then we have a pin fin right here, which is another non-uniform cross section right there in 3D, like this situation, like this here, like a cone. So the next thing we want to take a look at here is the fin equation. Now, there's a lot of assumptions we're going to have to make in order to utilize this general governing equation here for the Finn equation. What we're going to assume is that it's one-dimensional, steady-state conduction in an extended surface of constant conductivity our thermal conductivity K value there, and it also needs to have a uniform cross-sectional area, our A sub C, along with negligible generation, so our Q dot is equal to 0, and negligible radiation, so our Q double prime radiation is equal to 0. With all these assumptions, then we can use the Finn equation shown in the form here from equation 3.67 in our textbook right here. We have that d squared T over dx squared, second derivative with respect to our position x of our temperature, minus HP divided by our thermal conductivity K times that uniform cross-sectional area AC, all times the difference in our temperature between T minus T infinity, and this is equal to 0. So this again goes back to equation 3.67 in our textbook and is only valid with these assumptions that we mentioned above here. Or we can replace the bulk of this with the variable m squared. So if we replace this with m squared is approximately equal to our HP over our KAC right there for this relation right there, then we can, and the reduced temperature here is our theta is approximately equal to T minus T infinity right there. This reduces down to now, when we replace it like this here, a d squared theta over dx squared minus m squared theta is equal to 0, which with this reduction down there, that simplification with our m squared in there, this is now equation 3.69 in our textbook. So as we continue looking at the Finn equation here, what we want to do now is take a look at conduction and convection in a fin of uniform cross-section right here. So we talked about a couple different types of fins right here, and this is the simplest case here that we saw was for the uniform cross-section. We'll start with that first here. So within this we can see our diagram below, and we can see over here we have the base of our fin interface right there. At the base we can see that we have the temperature of the base, T sub B. We also have at that location there where the base of the fin intersects with the base over here, we have now this Q sub B is equal to Q sub F. The Q of the base is equal to Q of the fin at that interface right there where those two meet. Then we can see we have our conduction term right here for the fin itself. So we can see that this is an equation that we derived earlier, negative thermal conductivity times our cross-sectional area times that change in temperature with respect to x, that distance we're moving out in this way in our x direction right there, from where x is equal to L right there, where L is right there. So that is our x is equal to L. So this equation is for this position where x is equal to L at the end right there. Now we can also see we have our convection term over here. We have H times A sub C, that cross-sectional area, times the temperature difference between the temperature at the tip of this guy right here at L, when x is equal to L, minus the temperature of our surrounding fluid right here, which is our T sub infinity right there. Now within this we can see that the magnitude of the temperature gradient decreases with increasing x. So this is a trend is a consequence of the reduction in the conduction heat transfer, our Qx of x, with increasing x due to continuous convection losses from the fin surface. So next let's take a look at a couple different conditions. We're going to take a look at our base condition and our tip condition. Our base condition is when x is equal to 0. So if we come over here, moving over this way in our x direction right here, here's our 0 right there. So when x is equal to 0, this is right here is our T sub B right there. So we have this relationship here, theta of 0, so when x is 0 right here, this is equal to our temperature difference between the temperature at our base right here, when x is equal to 0, minus our T sub infinity, or our fluid temperature right here. And this is going to be what we're going to call our theta sub B. Now we want to take a look at the other end over here when x is equal to L. So if we move along x here, we get over to L right here. We're at the tip of our fin now when x is equal to L. So now for convection, when x is equal to L, we have the relationship here, negative thermal conductivity times our change in theta with x right here, d theta dx, when x is equal to L. This becomes h theta of L right there. So that's a relationship for convection. For adiabatic right here in part B, we can see our d theta dx when x is equal to L is equal to 0. And for a fixed temperature, we had a fixed temperature here, then our theta of L is equal to theta sub L. And last, for the infinite fin condition right here, when m sub L is greater than 2.65, remember this relationship for our m up here from previously, this is the infinite fin condition, infinite fin situation right here. So when we have an infinite fin, when m times L is greater than that 2.65, then we can say that our theta at L, when x is equal to L, is equal to 0 for the infinite fin, because we're going out infinitely right there, so that would make that equal to 0. So now we can take a look and reduce down our heat equation from general form. So here's the general form of our heat equation right there. But now we have this relationship at the tip condition when x is equal to L that we have for convection here, this k d theta dx, which there's our k d theta dx right there. We can replace this with h naught of L right there, so we can put that right in over here. So then what we have is we can reduce this down by those relationships there for equation 3.78 in our textbook right there, which says that Q sub F, or our fin heat rate, is equal to the integral over AF of h theta of x DAS, or the surface area of the fin. So now I want to take a minute and talk about this table 3.4 in our textbook here. This is a great reference. I know some of these equations are getting pretty involved, and there's some big assumptions and special cases and a lot of different relationships that we've had to memorize. So this is a great place to go and check for those there. So we have those 4 different cases we just talked about before, where we have convection heat transfer, adiabatic, prescribed temperature, and infinite fin. And this is all for temperature distribution and heat loss for fins of uniform cross-section. So we're just looking at this uniform cross-section here in table 3.4. So side note, these tables are great to reference back to, but make sure we read everything in the table so we know exactly what we're using and that we're using the right table. If we didn't have a uniform cross-section fin, this is not the right table for that. Also, a thing to note is a lot of these equations have been reduced down and simplified based on relationships that we can see. So if we go down in the footer of this table right here, we can see the relationship. Our thetas are t minus t infinity. Our theta sub b is equal to our theta of 0, when x is equal to 0, is equal to t sub b minus t infinity there. Our m squared, lowercase m squared, is this relationship here for our HP over our KAC. And our capital M now is the square root of HP KAC theta b. So all of these go in there, and that makes it easier in our table just to have a single variable in there rather than having all of this here and complicating even more, especially when we're talking about big equations like this that have a lot of those variables embedded in them there. So if we take a look here, I won't go through all these equations, but I highly recommend going back to your textbook and looking through this thoroughly and understanding when to apply these. And you can even see we have equation numbers next to them. So if you're doing out a homework problem or an exam problem, you can say I used equation 3.75 for my textbook here. You can reference back to that there. So within this here, we have case A. Let's just start with that there. We're dealing with convection heat transfer. So we have that general relationship that we've talked about a couple times now, that our H theta of L is equal to this negative K thermal conductivity times that change in theta, well, with respect to X. And again, we go down here, our theta is our change in temperature right here. So that's T minus T infinity right there. And this is when X is equal to L. Now for that case A right here, we're dealing with convection heat transfer right there. We can see our temperature distribution, or our theta over theta B, is given by this relationship shown here in equation 3.75 right there. We have some sines and cosines. And again, pay attention. You get your M. We can come down here. What is our M right there? Well, it's the square root of this right here if we don't need the square term of it. Then we have our L value. What is our L? Well, L is when X is equal to L at the end, the tip of that fin right there. There's our X right there. So going along the length of the fin from the base when X equals 0 to X is equal to L right there. Then H over our MK right there, our thermal conductivity, so on and so forth. We just double check that we make sure we know what we're plugging in for each of those variables. It may make sense to solve for them separately before we do that. So these are all of our governing equations that we're going to utilize right here for temperature distribution, heat loss for a uniform cross section. So now we're going to take a look at our fin performance parameters here. So in particular, we want to take a look at our fin efficiency right here. Where our eta sub f right here for our fin efficiency is equal to the ratio right here of our Q sub f, where Q sub f is the fin heat rate. This divided by our max fin heat rate there is equal to, when we plug in for our max fin heat rate relationship here, H times our AF, the area of the fin right there, times our theta sub b, which we've defined in the previous slide right here. And this is our relationship now that we can plug in for to find our eta sub f for the fin efficiency, where the fin efficiency is going to be between 0 and 1. This equation right here relates back to equation 3.91 in our textbook. Now for some common geometries, we can take a look at table 3.5 in our textbook, and it'll give us expressions for our eta sub f for those fin efficiencies for those common geometries. Let's take a look at one of those in particular here. Let's take a look at our triangular fin right here and see what type of expressions they're going to give for our fin efficiency, our eta sub f right here. So our eta sub f right here, our fin efficiency is equal to 1 over ml times our I sub 1 times 2 ml over I naught, or I 0, times 2 ml there. Now, when we get to our table in a minute here, we can take a look and recall that there are values for these m's right here that we can plug in for those from the table. Now we can also take a look at our A sub P. We can see this A sub P right here in a couple different relationships that we've seen throughout this chapter. This is our fin profile area right there. So for a triangle, the fin profile area we can see here is lowercase t over 2 times L. So this relates back to our diagram now over here. So we can see our t right here is that thickness at the base right there, that dimension there, and we can see that our L is this length going out this way right here. So our fin profile area we can see is this triangle right there. So we have this t over 2 times that L distance there to get that fin profile area there. Now, our A sub F is the surface area of the fin. So that's different than that there. The surface area of the top and bottom surfaces all along this right here. So this is equal to, our A sub F is equal to 2W, where W is that length right there. So it'll be base times height right there. So then we come out by the length of this right here on both those. This will be found by our L squared plus T over 2 squared, all to the 1/2 power. So let's not get these confused. Our A sub P is the fin profile area. So if I were to erase this here just for a second, we take a look now and we can say that our fin profile area is this right here for a fin, and for our surface area, A sub F right here, is the surface area of the fin, which is going to be the top and bottom layers right here, and there's one underneath as well. So make sure we keep track of those. And again, this will change for each different type of geometry. This is just specifically for our triangular fin that we have pictured right here. So continuing on with our fin performance parameters, now rather than looking at our fin efficiency, what we want to look at next is our fin effectiveness. So our fin effectiveness is given by our epsilon sub F variable right here, and this equals our Q sub F, where Q sub F is our fin heat rate, divided by H AC comma B over theta times theta B right there, where A sub C is the cross-sectional area right there. So what we can determine from this relationship in 3.86 in our textbook is our fin effectiveness, or our epsilon sub F right here, is going to increase with a decreasing H value. So if this decreases, this is going to cause this. Those are inversely proportional. But it's going to be directly proportional with our K value. So as our K value increases, this is going to increase. And as our A sub C over P relationship right here decreases, this is going to increase. So it's going to be inversely proportional to that as well. Now, the next thing I want to talk about as far as our performance parameters go is our fin resistance right here. So this is given by equation 3.97 in our textbook here, where our fin resistance is our R sub T comma F right here. And this is given by this relationship here over theta sub B over Q sub F. You can plug in a relationship for this here, which is equal to now our 1 over H times A sub F times our fin efficiency. So using this expression from up above here, we plug in for that there. We then get this relationship that we see here in 3.97. Based upon, if we've already calculated or know our fin efficiency, we can get our fin resistance right there with the all additional H and A sub F values. So we talked about the triangular fin shape right here. So here's some other efficiencies of common fin shapes that we may see. And here's this table 3.5 that we discussed in the previous slide right here. So we can also have our straight fins or rectangular right there. So we have a relationship for our A sub F based off the geometries given over here in our diagram right there, our L sub C and our A sub P right there. So this right here for our fin efficiency for rectangular is given by a relationship here as 3.94, where we have our fin efficiency equals the tangent of H times M times LC over MLC right there. We can also see we have a relationship here if we have the triangular. We have this relationship here for our fin efficiency given by 3.98. And for a parabolic shape right here, where we have this relationship for Y defined by this relationship here between T and X right there, along the length L, we have this equation 3.99 for our fin efficiency right here. And again, we can go through both the triangular and the parabolic and find our A sub F's and our A sub P values right there. We can also find our C1 relationship here to plug in for our A sub F's as well. And again, these are all referenced off of the dimensions shown over here in our diagram. So this is another great table. If we're looking for a particular type of geometry of a common fin shape, we can look it up, come here, and then get our equations and all the variables that we need to solve for that. So we can continue on with table 3.5 here. And again, the thing I want to note here at the bottom of table 3.5, we saw M in a couple of these equations over here for our fin efficiency. Well, this is our values for M's right here. So take a note down here. Always pay attention to those footnotes so we can know what to plug in correctly. And a couple other of these different fin geometries over here. So we could have a circular fin right here. So again, we have our A sub F and all of our variables there related back to our diagram here and our general equation for our fin efficiency by 3.96. We could also see the same for our pin fins. Again, with our governing equation for efficiency there. Triangular right there, so we can see this interesting shape right there and our associated fin efficiency equation, and our parabolic cone shape right over here, where we can see this kind of comes down right there by this relationship for Y right there. And again, our governing equation for our fin efficiency there. So again, 4 more different types of fin geometries for common shapes you might see. And if we need to get our efficiency relationships, we can reference back to this table. So far we've just talked about individual single fins of different geometries and shapes. Well, in reality, we're going to have a bunch of those, or an array of those. Let's talk about fin arrays. So this is representative arrays of, we can see here in part A, we have rectangular array of fins. So these we've seen for one of the more simpler geometries right here, but now we've got three of these right here that we've shown, at least in this diagram right here, and maybe even more than that. And within this, it brings in some other variables. So whether it's a rectangular or even these annular fins over here that we have in B, what we can see is the new thing we have here is the spacing, this S value between, the distance between the different fins that we have within our array. Other than that, we still have our base right here at the bottom right here. There's our temperature sub B at the base of the fins right there. There's the thickness of the fins right there like that. There's over here on this one, there's our temperature at the base right there. This one, the difference we also see here, we have our radius going out to the base from the center and our radius going out to the tip of the fin right there at the end length right there. And we also have the associated width and length of each of these fins, assuming they're all the same in the array there. And we have our convection term for our fluid temperature, T sub infinity, and our H value right there as well. But again, now we have this new variable showing the spacing between the fins within the array. So with multiple fins, we can expand upon some of these other equations and relationships we've seen before. So if we're talking about surface area, now what we're really interested in is our total surface area, or our A sub t. Or now we can come in with this variable n right here, which is the total number of fins, times the area of those fins, plus A sub b, because now we have the area in between there of the area of the exposed base, or the prime surface as well. So the total surface area is going to be the area of the fins, plus the area of the fins times the total number of fins plus the area of the exposed base right there, and that's going to give us our total surface area. So from there, we can then go into our total heat rate. So we have our Q sub T. Again, the N comes back for the total number of fins. We have our fin efficiency in there. We can add this all up here, and we can see this relationship can be reduced back down to our theta sub B over R sub T naught, where we've talked about our R sub T naught previously before for resistance, and we've talked about those before. But we can see this all reduces down to equation 3.105 in our textbook there if we plug in. So I would highly recommend going back to that, and they can go through the derivation process of how we can get there for our total heat right now. But the main difference now is we're talking about a total number of fins. So make sure we have that into account there as well. And the last thing we're going to talk about here with these fin arrays right here is our overall surface efficiency now. So we're talking about efficiency before, now we want the overall surface efficiency and our overall resistance as well. So this relates to equations 3.107 and 3.108 in our textbook, or 3.107 we can see here we have our overall surface efficiency, our eta sub 0 right there is equal to 1 minus that total number of fins times our A sub F over our A sub T now, where we now 3.104, we have the relationship for A sub T right there, times 1 minus the efficiency of each individual fin right there. So now this relates to equation 3.107 for the overall surface efficiency. And the same thing for resistance right here. The overall resistance right here is equal to our Q naught over B, so our theta B over Q sub T, which is equal to 1 over, now we have that overall surface efficiency they're plugging in at the bottom here times H times our A sub T, which again is that from equation 3.104 up top there. So we can plug all that in and get this equation now 3.108. So as we continue on with our fin arrays, we want to take a look at our equivalent thermal circuit. Now we want to do this for with and without contact resistance. So in part A here, we'll deal with it first without any contact resistance. Then in part B, we'll look at it with contact resistance. So you can see we have our fin over here. We have two fins in this example here. Here's our temperature at our base. Here's our temperature of our surrounding fluid, our H value there. Then we have our Q sub F, heat transfer for the fin, Q sub B, our heat transfer for the base right there. So then we can come over here and draw our thermal circuit right here from T sub B to T infinity right there. And we can see on the top here we have N for the number of fins. In this case, it'd be 2 for this example right there, times our N sub F, our fin efficiency, or eta sub F, our fin efficiency, times our H, times our A sub F, our surface area of the fin right there, all to the -1. Then on the bottom here of our circuit right here, we have our H value times A sub T minus N, the total number of fins, times our A sub F right there, all to the -1 right there. Now we can draw this out in another way right here, combine those, and we see our T sub B to T infinity right there. And we have our total heat transfer right there, Q sub T right there is equal to, on our circuit right there, our N naught right there, our eta naught right there, times our H times A sub T all to the -1. So that is our relationship in our thermal circuit right there without contact resistance. If we want to take into effect the surface contact resistance, it's going to be pretty similar, but now we can see we have this R double prime TC up here, our thermal contact resistance up there that we're taking into account as well. And that really is the only difference right here. We can see that that comes into factor right here on the top of our circuit where it wasn't there when we weren't looking at our contact resistance or considering it negligible. So that comes into play now there. The rest of it remains pretty similar. So we have that same type of circuit right there from T sub B to T sub infinity right there. And again, there's your temperature at your base. There's the temperature at your surrounding fluid over there. Your Q sub B from the base, Q sub F from the fin right there. So that comes down here and we can do the equivalent thermal circuit that we did in the diagram in part A. So now you can see we have this Q sub T in both of these in the diagram below for our thermal circuit right there. Well, we have an equation right here, a relationship for that Q sub T. So Q sub T is equal to the efficiency there times H times A sub T times theta B, which we can reduce down with some of the relationships we saw for our R sub T right there from before. So this is equal to, our Q sub T is equal to our theta B over R sub T comma 0 of C right there. So from that there, we can say, okay, well, what is this right here? How do we plug in for this right here? Well, this relationship is given by equation 3.110a in our textbook right here, where this is 1 minus our n, the total number of fins, times our area of the fin over the total area over here, times 1 minus our efficiency of each fin right there over C1 right there. Now we can see, well, what is our C1? Well, C1 is given by the relationship in 3.110b in our textbook right there, where C1 is equal to 1 plus that efficiency of the fin right there, times our A sub F right there for the area of the fin right there, times that contact resistance right there, all over A sub C comma B. And then we can say, well, what is our contact resistance right here? So we can go to our equation 3.09 right here, which RT of O right there, our thermal resistance right there, is equal to 1 over that. There's our N sub O, that relationship right there, times our H times our A sub T right there. So pay attention between these A sub T, A sub F. What do those mean as you plug into those? But you can see how these kind of all go into one another and plug into each other as we're going through these equations. Can get very confusing quickly. So as you're doing out your homework problems and your sample problems, be sure to write these down, say what your governing equation is, and don't just try to plug them all in one long involved equation. We'll plug into them individually, maybe get some numerical values that you can solve for and plug into the other general equations. So now let's take a look at a fin example problem here. So we'll take a look at problem 3.126. We have a turbine blades that are mounted on a rotating disc in a gas turbine engine that are exposed to a gas stream that is at, it gives us a temperature here of T infinity for our gas right there of 1200 degrees Celsius. And it maintains a convection coefficient of H is equal to 250 watts per meter squared times Kelvin over the blade. So we can see they give us a diagram down below here. Here's our rotating disc right here. We can see here's our fan blade right there. There's the tip of it there. We can see it has some length L. We can see our gas stream there going through as T infinity and H right there. And there's our air coolant right here as well. And our temperature at the base, T sub B. And we see X starts right here at the base at 0 right there and goes up to an L length up here for the length of the fin there. Now it tells us the material that the blades are made of. They're fabricated from Inconel right here. That gives us our value for that of K is equal to 20 watts per meter times Kelvin. It tells us it has that length of equal to 50 millimeters. So again, pay attention to our units right here. Everything else is in meters, is in millimeters. Make sure we do our conversion correctly. Now it also tells us the blade profile has a uniform cross-sectional area, and it gives us that as A sub C is equal to 6 times 10 to the negative fourth in units of meters squared. It has a perimeter, P is equal to 110 millimeters. A purpose blade cooling scheme, which involves rotating air through a supporting disc, is able to maintain the base of each blade at a temperature given to us now as our T sub B is equal to 300 degrees Celsius. So now with this problem here, they ask us to solve for two separate things in this. One, they ask us in part A if the maximum allowable blade temperature is at 1050 degrees Celsius. That tells us that our blade temperature right there, and the blade tip may be assumed to be adiabatic. Is the proposed cooling scheme satisfactory? So they need us to answer that question right there. Is this cooling scheme satisfactory for that? Part B, for the proposed cooling scheme, what is the rate at which the heat is transferred from each blade to the coolant? So we need to find that rate at which it is transferred there in part B. Now that we've had the opportunity to read through our problem statement and look at our initial given diagram, what we want to do next is create our setup page. So for our setup page here, I have the problem number right here, 3.126. This is a homework assignment. You'd have your name, the due date, what assignment it was up to here on the right. Then I have my section for all my given information here, and my simplified diagram over here where I have all my variables without any numeric values, so that you can see the variable names and come back over to the given and reference those. Down below that, we have all the information we're looking to solve for and any assumptions we're going to make. So we'll start here with our initial given diagram up here, simplified down. I can see I have my t sub infinity and my h value right there. So my t sub infinity right here is given to me in the problem statement as 1200 degrees Celsius. My h value right here is given to me as 250 in units of watts per meter squared times Kelvin. Then I also have over here for my conduction section here, I have my K value right here. My thermal conduction right here is K is equal to 20 watts per meters times Kelvin. I have my length right here. This is given to me as 50 millimeters, so I convert that to meters right away as 0.05 meters. I have my A sub C value right there, the cross-sectional area of the blade. So A sub C is equal to 6 times 10 to the negative fourth in meters squared. I have my P value right here. So my P, the perimeter, is 110 millimeters, or if I convert to meters, 0.11 meters right there. And then I have my T sub B, my temperature right down here, at the base right there, T sub B, is given to me as 300 degrees Celsius. Now, with all this, we need to solve for two separate things. Part A, we want to find the max temperature at x is equal to L. So when we get up here, our x is equal to 0 at the base. It goes up to here, x is equal to L at the tip of the blade right there. And then part B, we want to find the heat transfer from the blade to the coolant right there, which is our Q sub B, and we can see that drawn right here in our diagram there. Now, the assumptions that we're going to make down here, first, we're going to assume 1D steady state conduction in the blade. Then we're going to assume that it's going to be a constant K value. Then it's going to also have an adiabatic blade tip and negligible radiation. So now that we have this here, we can begin our solution. We can take a look through everything that we have in our given section, what they're asking us to solve for, any assumptions that we've made, and then come up with a plan for attack, procedure for analysis here, and take a look and see what our governing equations will be to solve this problem. So now we're going to express a couple of these different governing equations we'll utilize in the solution to this problem right here. The first equation we're going to look at here is equation 3.68 from page 158 in our textbook here. And this is for fins of uniform cross-sectional area. So we have that theta of x is equal to T of x minus T infinity, where T of x is the temperature at some distance x from where x is equal to 0 at the base of the fin right there, minus our surrounding fluid temperature, T sub infinity right there. Now for the case where x is equal to 0 right there, right at the base interface right there, that's where we have T sub b minus T infinity, because when x is equal to 0, that right there, if we look back at our diagram, is where we have our T sub b. So this will be T sub b minus our surrounding fluid temperature, T sub infinity, and this is going to be expressed by theta sub b. And this comes from equation 3.74 on page 159 of our text. Then we'll move on to take a look at equation 3.80 in our textbook here. We have the ratio of our theta over our theta sub b. And this is equal to the hyperbolic cosine of m times L minus x right there, where L is that distance all the way out the tip of the blade right there, all over the hyperbolic cosine of m times L right there. So now we're going to plug in our relationship here into that equation 3.80 in our textbook there for our theta and our theta sub b. Where theta we have right here T of x minus T infinity, which we saw on the previous slide for that derivation right there. And the bottom, when x is equal to 0, that is our theta sub b right there at the base. So this is T sub b, the temperature at the base, minus the temperature of our surrounding fluid, T sub infinity right there. Now this is equal to the right-hand side of our equation that we saw from 3.80, where we have the hyperbolic cosine of m times L minus x, all over the hyperbolic cosine of m times L right there. So now what we want to do as we continue on with our solution is plug in for x is equal to L. So we can do that. We go back up to this governing equation above here, and everywhere we see an x, we're going to plug in for the L right there. So what we have here on the left-hand side of the equation on our numerator, we have T of L minus T infinity, all over the bottom is still T sub b minus T infinity there, is equal to the right-hand side of the equation, hyperbolic cosine of m of L minus L. L, that simply becomes 0. The L minus L cancels out. That whole term goes to 0 right there. So we recall now that the hyperbolic cosine of 0 is equal to 1. So the whole numerator now becomes a 1 right there. Then on the bottom we have the hyperbolic cosine of m times L right there. So we reduce this down. We now see we have T of L minus T infinity all over TB minus T infinity is equal to 1 over hyperbolic cosine of ml right there. Where now we recall we have this relationship right here we've shown before that m squared is equal to h times p all over k times our AC right there. So if we want just m rather than m squared, we take the square root of both sides. We now see that m is equal to the square root of mp over k AC right there. So we can plug in known values to solve for our m right there before we plug that back into our other governing equation. It's always a good idea to do that if you have the capability of making this numeric value and making your governing equation a little bit less complicated. I would suggest going ahead and do that. Just make sure you do out your unit analysis correctly, double check that there, and make sure you carry out your decimal points to the appropriate number as well, and don't do any rounding off. So with this here, we can do that. M is equal to, well, we can plug in our known values right there. We have our H value of 250 watts per meter squared times Kelvin. I have my units included there. I have my P value right here of 0.11 meters. Then I have on the bottom here my K value of 20 watts per meters times Kelvin. And I have my A sub C in this here of 6 times 10 to the negative 4th meters squared, all to the 1/2 power there. You can plug and chug, do that by hand, calculator, Excel, MATLAB, your choice. M is equal to 47.87 m to the negative 1 right there. So we can plug that back in now for our ML right there. We see now we plug that in, we have that 47.87 in units of meters, 1 over meters right there, times 0.05 meters right there, which makes this unitless. 1 over meters and meters cancel out. So our ML in this case here is 2.39. So we can take that value right there for ML and go back up to our previous equation right here. And we can see now, okay, I can plug in for that there. So I have 1 over now the hyperbolic cosine of my ML right there. So I can plug in that value for that. But first, before we plug in any numeric values, let's rearrange this and solve this for T of L, because that's what we're looking for right here. So we're going to multiply this over to the other side over here, and then we're going to add in our T infinity right there. So we get TL on its own. So TL is equal to TB minus T infinity all over the hyperbolic cosine of ML, which we now have a numeric value for, plus our T infinity there. So the next step is we're going to go ahead and calculate this here as a whole term. So the hyperbolic cosine of 2.39, when we plug in for that value we just found for ML, is equal to 5.51. So I can now put this as a numeric value down here on the base right there. And then we can plug in the rest of our known values right here. So T of L is equal to, when I plug in for my T sub B, the temperature at the base of the fin right there is 300 degrees Celsius. My surrounding fluid temperature is given to me as 1200 degrees Celsius. And I also have now that 5.51 down there on the denominator for my hyperbolic cosine of 2.39 plus T infinity again, or T infinity is 1200 degrees Celsius right there. I do that all, everything is in Celsius, so that double checks. So T of L is equal to 1037 degrees Celsius. So that gave us our answer for the first part of the problem there for T of L. So now we want to move on to part B, the second part of the solution right here to this problem right here. With this, we need to find our fin heat transfer rate, and we can utilize equation 3.81 on page 161 of our textbook as our governing equation for this. So our Q sub F, or our heat transfer rate of the fin, is equal to right here, this is our M, our capital M. We can go back to table 3.4 in our textbook as well to double check this, is equal to the square root of HPKAC times our theta B times the hyperbolic tangent of our ML right there. Now, a lot of this we already have solved for the values part in part A. So let's just say where we have theta B is equal to, so this right here is equal to T sub B minus T infinity, and this is from equation 3.74. And then we can see down here our theta B is then would be equal to, well, our T sub B is 300 degrees Celsius and our T sub infinity is 1200 degrees Celsius. So therefore we have a numeric value for theta B, which is equal to negative 900 degrees Celsius. So now we have a value that we can plug back in there to that equation 3.81. So we'll start plugging in all of our known values right there. So we have our Q sub F right here that we're solving for right there. So this is H. Well, our H value was given to us as 250 watts per meter squared times H right there for our units values right there. Our perimeter was 0.11 meters. Our K value was given to us as 20 watts per meters times Kelvin. And our A sub C is given to us as 6 times 10 to the negative 4th meters squared. All of this to the 1/2 power right there, times our theta B, which we've just plugged in as our negative 900 degrees Celsius, times the hyperbolic tangent of, we can see here our ML right there. Well, now we have this value here for M if we take that back from our table right there, which is the square root of HP over KAC times our value for L right there. That is our value for Q sub F. So we can solve all of this, so we have the values for right here. Let's just get a numeric value for that. Plug that in. That ends up being negative 517 watts. Do out your unit analysis. Make sure that truly comes out in watts right there. Then we can deal with the right-hand side, because I know it gets a little funky there. So now we'll plug back in. We're looking at the hyperbolic tangent of our H right there is 250 watts per meter squared times Kelvin right there. And then we have over here our P value right there of 0.11 meters. Then we have down here on the bottom our K value of 20 watts per meter times Kelvin. And then we have over here our A sub C, which is 6 times 10 to the negative fourth meters squared. All of this to the 1/2 right there, times our L. Well, we have an L value out there. That's 0.5 meters. It was given to us in the problem statement right there. So that's a plug and chug. But again, do out your unit analysis. Make sure you put those in right. You didn't make any carry-through errors. Didn't read your writing wrong. And then you end up with a value here now for this section over here of 0.983. So we can plug that in. So it's 0.983 times our negative 517 watts right there. So our Q sub F right there, because this is unitless, these all cancel out for this right-hand term over here. So our Q sub F is equal to a negative 508 watts right there. And our Q sub B is equal to negative Q sub F. So our Q sub B is equal to 508 watts for part B of this problem.